Hello everyone, I'm njwildberger and welcome to Algebraic Calculus. In today's video we're going to look at polynomials from a new point of view. We're going to introduce things called polynumbers, which are a kind of variant or more precise way of thinking about what a polynomial is. So we're going to move from the traditional view of vectors as n-tuples and polynomials as expressions in some variable x. We're going to move from that to a more precise understanding, which is going to be encoded by these new kinds of objects called vexels, which are going to replace vectors, and polynumbers, which are going to replace polynomials for us. So what we want to do here is introduce these kinds of objects, polynumbers, in a more precise way, focusing on the computational aspects of things coming from data structures. In particular, we're going to be interested in the role of multisets and also, to a certain extent, lists. So let me remind you about the basic number systems that we're using. The natural numbers, which for us are going to include 0. So 0, 1, 2, 3, these are the counting numbers. And their extension, the integers, where we also include the negative numbers -1, -2, -3, and so on. So we're going to assume that we all have a working understanding of the arithmetic of natural numbers and integers. And it turns out that a lot of the things that we're going to say also extends to rational numbers, but for now it's probably safe for you just to think about natural numbers and integers as being the framework that we're talking about. Okay, so let's introduce some simple kinds of objects using some data structure ideas. The first is a singleton. Let's introduce the idea of a singleton, that it's a one list consisting of a single natural number. So a one list, by that I mean a list with one element. So it's got square brackets and it has a natural number in it, and that's all. So that object, we'll call that a singleton. Just give it a name. It's a lot like a natural number, isn't it? But it's a little bit different because it has this bracket bounding it. So it's not actually a natural number. It's a natural number in a box, if you like. Okay, so that's a singleton. And then we define a vexel to be an M-set, which is my preferred shortcut for the word multiset. So a vexel is an M-set of singletons. In other words, it's a multiset. It's a collection which is unordered and in which repetitions are allowed. And the objects here all have to be these singletons that we've just defined up here. So here's a vexel V. It contains the singleton 0, singleton 1, the singleton 0, the singleton 4, the singleton 4, the singleton 0. And the order doesn't matter. If we interchange these two, it would still be the same vexel. There's no commas. That means it's unordered. And repetitions, as you can see, are allowed. There's 3 singleton 0s and there's 2 singleton 4s. Now, to such a vexel, we can associate also a list. List because the singletons that we're using are naturally ordered, starting with the singleton 0 and then the singleton 1 and so on. So one way of writing down what's going on here is to record the number of times, or the multiplicity, of the various singletons that appear. So we get what we might call a multiplicity list, which records how many singletons of each type there are in the vexel. So this vexel here, we could associate to that the following list, starting with 3, telling us that there are 3 singleton 0s, then a 1, telling us there's a single singleton 1, and then a 0, there's no singleton 2s, there's no singleton 3s, and then there are 2 singleton 4s. So this list essentially encodes the same information as this multiset. They're almost equivalent, so they're sort of different ways of describing the same collection. But I'd like to think of this as being sort of the primary object, and this is a kind of descriptive form of it. Note that this multiplicity list is a little bit ambiguous because somebody else could come along and say, well, what about how many 5s there are? How many singleton 5s are there? There's 0 singleton 5, so we could also record that. And fair enough, we could. So we could add a 0 there and argue that this is also the multiplicity list for this thing. So a multiplicity list is Not exactly unique if we're willing to allow ourselves to append zeros, sort of unnecessary zeros, but they could be there at the end. So we have singletons and we have vexels, purely in terms of natural numbers and little data structures formed from them. The modern student of mathematics is used to the idea that sets are the fundamental building blocks of mathematics, but from our point of view, that's far too limiting and imprecise. Multisets are also good objects to build up mathematics, but I don't want to pretend that we have a theory of multisets. Okay, it's not as if we've defined multisets in some great generality. Rather, what we'd like to do is talk about small multisets that are very specific and we have complete control over them. And once we've mastered them, we can think about some bigger collection of multisets and so on. But nevertheless, there's some general principles that will apply informally to most multisets that we're able to enunciate. And one of the most important ones is this fundamental idea that there's an operation on multisets that is really a core operation in mathematics and responsible for arithmetical structure in a lot of different places once you sort of are in tune to it. And that's that multisets can be added. So if I have a bunch of multisets, think of them as boxes containing stuff, then I can combine the contents of these various boxes into a bigger box. I can dump the various constituent multisets out, and then I get all the contents in a new box. I basically added the contents of all the original multisets. This is an addition, and it's a very fundamental kind of operation. And so whenever we have multisets, we're in a position that we can perform this operation. So in particular, we can add vexels, because vexels are m sets of singletons, and if we add m sets of singletons, we're going to get other m sets of singletons. For example, here's a vexel containing the singleton 0, 0, 4, and 2. Here's another one w containing 1, 0, 0, and another one u containing 2, 2, 4, and 4. So we could add up all of these three. V plus W plus U. We take V, W, and U, we just put them all in the big box. So what do we get? Well, we get a big multiset which contains a 0, a 0, a 4, a 2, a 1, a 0, a 0, a 2, a 2, a 4, and a 4. There's no special need to organize anything because multisets are intrinsically unordered. But if we do want to start thinking about such a thing a little bit more comprehensively, then it makes sense for us to use a little bit of extra structure, namely the fact that if we can add multisets, then we can take multiples of multisets. Right? If we can add A to B, then we can add A to A. So we can talk about 2A or 3A or 4A if A is a multiset. And in particular, we can introduce sort of the most simple kinds of vexels, which are these vexels we might call E sub n, which are the vexels containing just one singleton, the singleton n. So let's define E sub n to be the vexel, which is the multiset containing a single singleton n. Right, then this vexel here can be more succinctly written as 4 times the multiset consisting of the singleton 0, because there's 1, 2, 3, 4 zeros, plus the multiset with a singleton 1, plus 3 times the vexel containing a singleton 2, plus 3 times the one containing a singleton 4. And this thing here is E0, this thing here is E1, this is E2, and this is E4, so we can write V plus W plus U as a linear combination of these basis vexels, 4E0 plus E1 plus 3E2 plus 3E4. So we have a little algebra of vexels. We can add them, we can take linear combinations, we have particularly pleasant basis vexels. Now, the coefficients in those linear combinations that we've just been considering are natural numbers. But it's not too hard to sort of extend this theory so that we have more general coefficients and so that our arithmetic is a little bit more general. So we can consider integral and then even rational vexels. And sort of one way of proceeding is to concentrate on these basis vexels that we've just introduced, E0, E1, and E2. And if we think of them as sort of the basic building blocks, then algebraically there's not much preventing us from considering combinations like this, 3E0 minus 2E4 plus E5. Now you might well ask, well, what kind of a vexel is that? What kind of a multiset is that if there's minus 2E4s? Well, one way of expressing that would be to write, here's the three singleton zeros, here's a singleton 5, and here are the singleton 4s, but with bars over them, which I like to call this sort of the anti-operation, which you can think of it as an accounting device that tells us that we really need to take the negatives of those. It's like things being in the red as opposed to being in the black from an accounting point of view. And you might say, well, what does it mean to have, minus 2 singletons? Well, that's the same kind of question that people used to ask about negative numbers. What does it mean to have minus 2 cows? That surely can't make any sense. Negative numbers are nonsense. But these days, we all appreciate that negative numbers are useful, even if, answering the question, what is minus 2 cows meaning? Well, there's indirect ways of answering that question, and really the same kinds of answers can apply here to make sense of what this means. But if nothing else, we can think of them as being formal combinations. And once we do that, then there's not much preventing us from going a step further and considering vexels with coefficients which are rational numbers. For example, 2E0 plus 1/2 E1 minus 2/3 E3. Which, if we had to, we could perhaps write something down like this. There's the 2 0 singletons. There's the 1 singleton, but there's only a half of it. And there's the E3 singleton, but it's got an anti over it, so it's sort of the negative of it. And there's only 2/3 of it. Okay, so, this is a kind of a multiset theory where we're considering fractional parts of things, but there's still a valid sort of justification for that, and it's not without application, certainly, to consider partial things. I own 2/3 of that share, and I own 1/2 of that piece of land, etc. Okay. So we can have a reasonably flexible algebraic framework of vexels with natural number coefficients, or maybe integer coefficients, or if we want, even rational number coefficients. Now, there's a lot more that we could say about vexels because they're very important in linear algebra and in geometry. Vexels can be added. We can take scalar multiples. We can take linear combinations of vexels. So we get linear spaces of vexels, and it's a very flexible notion. But what we want to do today is use this framework to go in the direction of polynomials and introduce these things called polynumbers. So what is a polynumber? A polynumber is a vexel. That's basically what it is. It's a vexel. But together with a special additional operation that vexels don't have. So when we consider polynumbers, we're considering vexels together with a further multiplication. So we're going to be able to multiply two vexels. And the multiplication is really quite simple and almost naive. Okay? So a vexel is an M set of singletons. So here's one vexel, and here's another vexel. This one has a lot of singletons. This one has a lot of singletons. How are we going to multiply these two vexels? What we're going to do is we're going to take products of singletons. So we're going to define the product at the level of singletons. And once we've done that, then we're going to take what's called the M set extension of this singleton multiplication. In other words, we're going to agree that we're just going to take the M set consisting of all possible products between the singletons in the first vexel and the singletons in the second vexel. All possible products of singletons. And so we need to know, well, how are we going to define the product of singletons? And here is the definition of the product of singletons in this context. So here's a singleton n. Here's a singleton m. These are natural numbers. That is like 0, 1, 2, 3, 4, etc. And we're going to define the product of these two singletons to be the singleton n plus m. So we're going to use the additive structure of the natural numbers to define the multiplicative structure of these singletons. And then if we have two polynumbers, in other words, vexels, say p, which is this one, and q, which is this one. P has a singleton 0, a 1, a 3, and a 1. Q has a singleton 2. There's another singleton 2, and there's a singleton 1. So we want to multiply these two polynumbers. Then their product PQ is what? It's the multiset consisting of all possible products between these four singletons and these three singletons. So altogether we should have 12 different constituents of this big M set. The singleton 0 times the singleton 2, well, that's the singleton 2. The singleton 0 times the singleton 2, that's the singleton 2. The singleton 0 times the singleton 1, that's the singleton 1. Okay, now we have to multiply this one times all of these. Well, we get 3, and then 3, and then 2. And then when we multiply these 3 by 3, we get 5, 5, and 4. And when we multiply by 1, we get 3, 3, and 2. So we've multiplied each singleton here by each singleton here, recorded all 12 results, and used this basic multiplication of singletons, which is really just addition of the corresponding natural numbers, over and over again. Okay, in terms of maybe more succinct basis representation, P0 is E0 plus 2E1 plus E3. Q is E1 plus 2E2. In terms of those, we could also write it down if we sort of realize that this law is telling us that E sub n times E sub m is going to be E sub n plus m. And so another way of doing this multiplication is to say, okay, it's E0 times E1, that's going to be E1. And then how many E2s are going to be? There's going to be an E0 times 2E2, that's going to be 2 E2s. But this 2E1 times this E1 is also going to give us a 2E2. So we're going to get 4 E2s altogether. How many E3s are we going to get? We get E3s by taking these E2s and multiplying by these E1s. So it's 4 of them altogether. How do we get an E4? We get an E4 by multiplying an E1 by an E3. I guess that's the only way. And how do we get an E5? Just by multiplying the E3 with the 2E2, getting 2E5. So that's how you multiply polynumbers. You multiply polynumbers. Polynumbers are just vexels, that is, they're m sets of singletons, and you multiply the polynumbers by just taking all possible products of the singletons in the two m sets. This is the kind of thing that a computer would love. It's very simple for a computer to do this. Very simple for a computer to understand, to code what's going on here. The objects are very simple. You just go through, you do all the things, and you spit it out. But it's also conceptually simple because it turns out that the properties of the algebra of polynumbers this way is very easy to appreciate and understand because the fundamental core multiplication is so very simple. Now I want to introduce some nice convenient notation for polynumbers that distinguishes them a little bit from vectors or vexels. So we want to write things vertically. So here is a polynumber. It's a vexel. Singleton 0, singleton 1, singleton 3, singleton 1. And here's the multiplicity list for it. But it's now written vertically, starting from the top down. Okay, notice this little bracket here. It's just what I use to alert us to the fact that we're talking about a polynumber and not something else. Okay, so this tells us that we have one singleton 0. We have two singleton 1s. We have 0 singleton 2s, and we have 1 singleton 3. That's a multiplicity list. That's a way of representing a polynumber. So if I write down a polynumber typically, this is the way I'd like to write it down. Now notice that there's a little bit of ambiguity here because we've said that this multiplicity list is not entirely unique, because we could say, but wait a minute, there's also 0 singleton 4s. So we could add a 0 underneath there and it would still be a valid description of this polynumber. So how many things we actually write down is a little bit, up in the air if we allow ourselves this possibility of writing additional zeros. Okay, so in this framework with this notation, here's what a typical polynumber looks like. Here are 2 of them, A0, A1, A2, etc., B0, B1, B2, etc. When I write the 3 dots, I mean it goes on in some fashion, but it doesn't go on forever. It stops because they are multisets. You have to be able to write them down, right? So they're necessarily finite. And how do we add them? Well, we add them just by doing addition of m sets, and so the multiplicities add, so the number of singleton zeros that we get is going to be the sum of the number of singleton zeros in each of the constituents, and same with the singleton ones and singleton twos, etc. So the addition is just component-wise, and similarly subtraction is also component-wise. So here's a 0, A1, A2 minus B0, B1, B2, etc. We get the polynumber A0 minus B0, A1 minus B1, A2 minus B2, and so on. So in this sort of vertical format, addition and subtraction are just the obvious component-wise operations. But multiplication is quite a bit trickier. So let's have a good close look at how multiplication goes when we're writing our polynumbers as vertical multiplicity lists. Here's A0, A1, A2, A3. Here's B0, B1, B2, B3. And I remind you this A0 means that the M set that we're really talking about has A0 singleton zeros in it. And this is the number of singleton ones. This is the number of singleton twos, etc. Okay, here's the product. The entry in the top part is the number of singleton zeros that the product has. How do we get singleton zeros? The only way of getting singleton zeros is to take a singleton zero from this thing and multiply it by the singleton zero from this one, because singleton 0 times singleton 0 is singleton 0 plus 0, which is singleton 0. So we're going to get A0 times B0 as the number of possible singleton 0 outcomes. How many singleton 1 outcomes are we going to get? Well, how can we get a singleton 1 outcome? We can get an outcome by taking a singleton 0 here and multiplying it by a singleton 1 here, of which there's A0 times B1 different possible combinations. Or we could take a singleton 1 from here and a singleton 0 from here, from which there's A1 times B0 possible combinations. Remember, we have to take all of the possible products between the singleton 1s here and the singleton 0s here. If there's A1 of them here and there's B0 there, then altogether there's A1 times B0 possible different products we can take. So the total number of singleton 1s that result is A0 times B1 plus A1 B0. For a singleton 2s, how can we get a singleton 2? Well, we can take a singleton 0 and multiply it by a singleton 2. That's the number of ways we can do that. Or we can take a singleton 1 from here and a singleton 1 from there. Their product will also be a singleton 2. And this is how many ways there are of doing that. Or we can take a singleton 2 from here and a singleton 0 from here, and that's the number of ways of doing that. And then the pattern is pretty clear. The number of singleton 3s, well, is A0 times B3 plus A1 B2 plus A2 B1 plus A3 B0, and so on. This is sometimes called a Cauchy product of these polynomials or sequences. Now, this is a reasonably sophisticated kind of operation when you look at it from this point of view, right? When we looked at it from the point of view of just singletons, it was very simple-minded. But when we think about it from the point of view of multiplicity lists, it's more subtle. And it's not entirely so obvious if you started with this definition why it should be that, for example, it's associative. The key property of this multiplication is that it's associative. If you have 3 polynumbers, P, Q, and R, you multiply P times Q first, using this, and then you multiply by R. It's the same as multiplying P by the product of Q and R. The reason for that is because the fundamental multiplication of singletons, just at the singleton level, is associative. the singleton n times the singleton m times the singleton k. This is going to be n plus m, and then when you multiply it by that, you're going to get n plus m plus k. But that's the same as multiplying the singleton n by the product here. This is m plus k, and this is n plus m plus k. So the associativity of ordinary addition tells us that this multiplication of singletons is associative. And then it's not too hard to see that because we're taking an m-set multiplication, the m-set multiplication is sort of automatically associative if the ingredient constituent multiplication between the actual objects is associative. And similarly, it's then not too hard to see that the distributive property is going to be satisfied as well, because that's also automatic whenever you have a multiplication of m-sets defined in this product of these guys by product of these guys fashion. So in some sense, we're getting some fundamental properties of polynomial or polynumber arithmetic sort of for free, or almost for free, because of the way we set things up using these rather foundational multisets to frame everything. It's a really powerful, simple-minded, kind of computer science-y point of view. That's, I think, quite attractive. Now I want to show you something of a clever trick that can be used to actually explicitly do polynumber multiplication. If you actually had to do a lot of these things, this is quite a useful technology if you had to do things by hand. And in fact, it's actually a trick that's reasonably well known in accounting circles, or at least it used to be when people had to do things by hand more. So here's an example. Suppose that we want to multiply this polynumber, 1 minus 1, 3, 2, times this polynumber, 4, 2, 1, minus 5. So here's the result. And so if you remember the rule, it's like 1 times 4 is 4. And then this minus 2 is the product 1 times 2 plus minus 1 times 4, and so on. But I want to show you now a slightly different way, which we might call the reverse strip method. So for that, I'm going to copy these things over here on these strips. So there's the second one, 4, 2, 1, minus 5. And the first one I'm going to copy, but in a slightly novel fashion. I'm going to exhibit it like this. You see, I've put it upside down. So it reads 1 from the bottom, then minus 1, then 3, then 2. Okay, so the way we multiply these things is we start like this. We put this up here like this. So the bottom entry there is lined with the top entry there. And so the only thing that we kind of see in common are the 1 and the 4. So the 1 times 4 is 4. Okay, now for the next entry, we just move this thing down 1. And now these are aligned and these are also aligned. So we have the product 2 and the product minus 4. It's the same products we had over here, but now we kind of see them more clearly. So 2 plus minus 4 is a total of minus 2, so we write minus 2. And the next one, we go down 1. Now we have 3 alignments. We get a product of 1, a product of minus 2, and a product of 12 for a total of 11. So we write down 11. And then we go down 1 more. Now we see product minus 5, minus 1, that's minus 6, plus 6, that's 0, plus 8, so that's a total of 8. Down 1 more. Now, yeah, up here there's really a 0, so this product doesn't contribute. We have a 4, a 3, a 5, and this is going to be 0 again. So we say 4, 3, and 5, that's 12. And 1 more. Now we have a 2 and a minus 15. That gives us a minus 13. Just taking the sum of those products. And then 1 more. 2 times minus 5 is minus 10. And if we kept on going, well, now there's no common things, so there's only zeros here and zeros here, so all the products are 0. So that's the reverse strip technology. So if you actually had to multiply big polynomials by hand, this is actually not an unreasonable technology to use. And so now let me finish by introducing the alpha notation, which is sort of my preferred casual way of writing down polynumbers, where we introduce a symbol alpha to represent a particular polynumber. So alpha is a particular polynumber. It is the polynumber E1. In other words, it's a vexel consisting of a singleton 1. Just one singleton 1. That's E1. We're going to call that alpha. Now, if you square alpha, then we're talking about E1 times E1, which is E2, which is the Singleton 2. Alpha cubed will be E2 times E1, which is E3, which is the Singleton, or the Vexel actually, consisting of the Singleton 3. And so it goes. So powers of alpha just pick up all the basis elements, with the exception of E0, and let's agree that alpha to the 0, by that we mean E0, which is the one that's so far not on the list. That's the Singleton 0 as a Vexel. Well, then any polynumber is going to be an expression in terms of these powers of alpha, because we're running through all the basis elements. So for example, here's a polynumber, a0, a1 up to some an. We can now write it as a0 times, well, alpha to the 0, which we'll typically just write as a0, plus a1 alpha. So this is a1 times e1, but instead of writing e1, I'm writing alpha, plus a2 alpha squared, all the way up to an times alpha to the n. So now we touch base with the usual theory of polynomials. So we recognize, aha, this actually is a polynomial. But it's a polynomial in this thing called alpha, but alpha is no longer some mysterious variable. We know exactly what alpha is. It's a data structure which is exactly this. This is exactly what alpha is. It's a square bracket which contains a square bracket contains a 1. So it's a Vexel consisting of the Singleton 1. Singleton 1 is a list which has one element, namely the number 1. So this is our way of avoiding entirely this delicate question of what do we mean by variables? What does the variable x mean? What does the variable t mean? What does the variable alpha mean? Now we know exactly what alpha means. Okay, we know. And we have a nice theory of polynomials or polynumbers, which is firmly rooted in data structures. So this is an overview. We're going to see that these polynumbers really help us with a lot of things. And as we go deeper in the calculus, we're going to rely more and more and more on the algebra of polynumbers. It's like a workhorse for calculus. We're going to, in some sense, leave numbers behind. Numbers are going to be almost trivial for us. And it's really polynumbers that we're going to be working with a lot. And then eventually we're going to have our eye on what happens if we try to extend these polynumbers and have sequences which carry on in some fashion. How do we possibly set that kind of thing up? That's going to be a very big challenge that looms ahead of us at some point. So there's much to learn. I'm njwildberger. Thanks for listening.